Classifying systems of equations. Systems of linear equations can be classified according to their solutions. And we know that a system of two linear equations will have one solution, right, if they intersect in one point, no solutions if they're parallel, or infinitely many solutions if they are the same line. If no common solution exists, right, and the lines are parallel, the system is called inconsistent. If infinitely many solutions exist, we call that system dependent. So sometimes the pictures help us. In the typical case, two lines will intersect in a single point. There'll be exactly one solution, and we call this system of equations consistent because the two lines intersect, and independent because they are different lines that just intersect in one point. We call it consistent and independent. Now, in the middle system of equations, one line is basically on top of the other. There are infinitely many solutions. Because the lines do intersect, we call them consistent, and dependent because they are the same line. In the last system of equations, these lines are parallel. They will never intersect. So there is no solution. We call this system of equations inconsistent. So let's look at an example, an algebraic example of inconsistent systems. Here we're asked to solve a system of equations. And we notice that the second equation, y equals 3x. So we could take that expression for y, the 3x, and substitute it in place of y in the first example. We end up with 0 equals -4. Now we know that's a false statement. And so algebraically, when we get something like this, which is a blatantly false statement, we know that graphically that means these lines will never intersect. Therefore, there is no solution, and that is why we call this system of equations inconsistent. And again, algebraically, it's when we end up with a false statement. Okay, now in the case of the lines that are one and the same, we'll start with a system of equations which at first glance, these lines do not look like they're the same line. So we could, if we wanted to, write both lines in slope-intercept form. Y equals mx plus b. Now the second line is in slope-intercept form. But the first one, we have to divide all three terms by 3. Now we have here the two lines rewritten in slope-intercept form, and when we look at them, we realize these lines are actually one and the same. They have the same y-intercept and the same slope. So because these lines are the same, there are infinitely many solutions, and this is why we call this system consistent and dependent. So again, algebraically, when we write both lines in slope-intercept form and we realize they are the same line, we call them consistent and dependent. Right now, here in this example, we're asked to classify the systems. In other words, does this system have one solution, no solutions, or infinitely many solutions? So the first thing we notice is, if I were to multiply this equation by 4, my y coefficient will become -1, which will be nice when I combine this or add this equation to the second one, because you'll notice if I add these two equations together, the y terms will eliminate, and I'm left with 6x equals 4, or x equals 2/3. So that is the x coordinate of the point of intersection. Now I take this x coordinate and I substitute it in place of x for either of the two given equations. And I'm going to multiply 2 times 2/3 plus y equals 1. 4/3 plus y equals 1. We'll subtract 4/3 from both sides. 4/3 taken away from 3/3 is negative 1/3. So I do have a point of intersection, namely 2/3 comma negative 1/3. So because there's exactly one solution, we call this system consistent and independent.